Shall we continue in 15.2 and 15.3? So this is double integrals over what we call a general region, and then we'll talk about area. So we just described Fubini's theorem. So there's some hypothesis here we didn't actually go over. But basically f is a continuous function in a region. And then it shows here that you can interchange the limits of integration. So now we want to talk about a general region. So go ahead and write this up. You can pause it or whatever to do that. So, but I'll go through it. It saves a little time. So we have our functions g. We'll call it g1 to g2. And it's implied in the picture, but basically we have g1 of x is less than g2 of x for all x in whatever interval we're talking about. So this interval would be from A to B. Actually, they can be equal in certain spots, essentially. And we'll get into that detail, but so if you have that and you integrate from G1 to G2, so it's like you're doing this, that's how I kind of picture it, and then you're going to add up that difference from A to B, and then this is your function value. So if this function, picture this function value above this region. So I can't show you here, but it's above the region. So you could have some region that's up here, and then you're integrating over this region down here. So then these functions, let me zoom in a little bit. This could be your G2, and this one down here like your G1, although this wouldn't work because they're not it's not a function. It wouldn't quite work like that. I'd have to draw that a little differently. So it'd be like this one, and then like this one, and then this is what you're going up to. But what we're going to focus on, though, so it looks kind of like that. So this would be like your G2, and this one would be like your G1. What we're going to focus on is kind of area for now. But we call this, this is like the first case, G1 to G2. The second case is going the other direction, going across. And we call this H1 to H2. So we're going from here to here. And then we're going to add up all these pieces all the way across from C to D. So this is what it would look like. Integral from H1 to H2 and then C to D. So this direction, and I kind of forgot to say that, the critical part here is this is dy dx when you're going our normal direction. If you're going the other way, then it's dx dy. You do dx first. And write this down, we'll write all this down, but make sure you say this. This is very critical, that the outside limit must be let's do it like that. I guess that was okay. So the outside limit, I'm trying to highlight this for us, must be constant for this to work. That's how you know you did it right. If when you set things up and this outside limit is a constant, then it'll be integrable, or you get an actual value. So keep an eye out for that, and I'll reiterate that as we go. All right, so those are the general setups. We call it sometimes type 1 and type 2 regions, just to describe it. So now let's go to some examples. We'll jump right into some examples. One of the critical aspects is to draw the region when you do this. So let me show you what I mean. So let's evaluate. Let me move this all the way up so I have more room to write. So next, let's look at these examples. So evaluate the double integral from x squared to 2x, and then 0 to 2, and then you have a function x cubed plus 4y dy dx. So first thing you want to do or think about here is sketch the region and limits of integration. So you want to look at and sketch those limits of integration here and here. So you can picture this then as y equals, let me do it like in gray or something. So you can think of it as like y equals x squared because it's y, to y equals 2x. So we want to sketch those regions first, and I will actually ask you to do that. Usually say sketch the region in question. So this region will look something like this. So you do your sketch. So it's we'll do it 1 and then 2. So 2, you're up at 1, 2, 3, and I'm going to have to move that down, of course. I always have something to fix. Okay, so we'll go to, we'll call this 1, and this is 2, and then 1, 2, 3, and then we'll go to 4. Go and erase this, bring this up higher. So we can get a better sketch. So y equals x squared, you go through 1, 1, and then 2, 4. So it may look something like this. So it comes down like this, something like this, and then it goes like this, and it's going to go all the way up. And I'm not happy with that. I'm going to have to do that over. Let's try that again. Okay, so there's our x squared. And this side doesn't matter. I'm just going to put it in there like that. And it goes up like this. And then y equals 2x will be over 2. So y-intercept would be 0. And then you're up 1, 2 over 1. And then 1, 2 over 1. So here's the intersection. And you can see that that's 2. That's what we kind of knew already. Like that. Okay. So this is your y equals 2x. And this is your y equals x squared. So you're integrating. So your bottom function is here, and your top function is here. So you're going from x squared to 2x, and you can see that the limits are 0 to 2. 0 to 2. So you're going all the way across. So we want to do a representative rectangle, or write in a representative rectangle, which would look like this. This is like the little rectangular piece that you're integrating across. Like that. And you add those up from left to right. But now there's a function here that we don't really need to know what it looks like. And it might go negative, so you're not really getting volume. If this was always positive above this region R, then you'd get volume. But for now, it's just basically it's just an operation to take that integral. So now we're ready to take the integral. So first you integrate with respect to y. So you get, this is equal to integral from 0 to 2. And then we take the integral with respect to y. So it's just x cubed y plus, and then we'll be adding one and dividing, so it'll be a 2y squared. And then you're going to evaluate that from x squared to 2x dx. So now what you're substituting in is your 2x and your x squared. So that equals the integral from 0 to 2, and it'll be x cubed, and then you get 2x plus 2 times 2x squared minus, and then now substitute in the x squared, so it's x cubed, and just make this into a bracket, try to make it clear what I'm looking at. So it'll be so top minus bottom, right? So there's x cubed, x squared plus 2 times x squared squared. And then you say dy. So then you want to simplify that completely. So you're gonna get x to the 5th plus 2x to the 4th. Simplify it. Integral from 0 to 2. So this is 2x to the 4th plus, that'll be a 4 times 2 is 8 x squared minus x to the 5th minus 2x to the 4th. And then you still say dx. There should have been an x back here. So dx. So we can see here that those are gone. And then you just get this equal to the integral from 0 to 2, 8x squared minus x to the 5th dx. And so now you're back down to a single variable, and you can simplify and finish that. Okay, so this time I will work it out a little bit. So you get 8/3 x cubed minus 1/6 x to the 6th, and then you're going to evaluate that as usual from 0 to 2. Since it's just a polynomial, when you put in 0, you'll get 0. So you're just evaluating at the 2, basically. So it's 8/3 2 cubed minus 1/6 2 to the 6th. Then you evaluate that. I'll let you finish the details. You get 32 thirds. All right, so that's one example or type of examples that we will do. Let's see, we'll do another